Okay, so in the previous videos, we went through the main mechanism of electrophilic aromatic substitution, and we were able to use that to add a couple functional groups to an aromatic ring, and we kind of talked about the three basic steps in electrophilic aromatic substitution, that is, generating an electrophile, and then attaching it to the ring, and then reforming the ring, right? And so we talked about how we have to generate a really, really good electrophile for an aromatic ring to want to reach out and grab, to temporarily break its aromatic ring before it gets reformed at the end. And, but if we think about it, we've been dealing with a really good electrophile all along, right? And that's our good old buddy, the carbocation, right? And so if we can generate a carbocation, then we should be able to add that carbocation to the aromatic ring. And that's in fact what does happen. What we're going to be looking at then is Friedel, Friedel crafts alkylation, right? So Friedel crafts alkylation. This is just one of the standard reactions that every organic chemistry class covers, right? This is your quintessential reaction for adding alkyl chains. Wow, chans. Swing and a miss. All right, chains to rings. Okay, aromatic rings. Okay. There are some limitations with this. We'll talk about that as we go along, but this is kind of your go-to method. Forms cations, right, along the way, aka, as we are looking at the mechanism, we will see a cation. Now I have to stop right here, okay? I have to stop right here. Okay. It's been maybe a while since we really, seriously dealt with a lot of carbocations and all this kind of stuff. I know we did a lot of it in the first semester, and here we are back with our good old buddy, the carbocation, okay? You can't forget everything that we talked about the carbocations. The exact same ideas are going to be at play here. We're going to be generating carbocations again, right? They're not going to be any different, right? I should be careful here. For the most part, one carbocation is the same as the other, all else being equal, right? What I mean is a tertiary carbocation is the same as a tertiary carbocation under all conditions, right? A primary cation is the same as a primary cation, everything else being the same. And so the point that I'm just trying to get you guys to do is remember what we know about cations and how they form and how they react and how they can rearrange and how they can shuffle and when they do want to form and when they don't want to form and all that stuff that goes together to really talking about how a cation can behave. All right? So all that stuff, all those ideas that we learned about in the first semester are going to be at play here again, okay? And that's what I mean with that there are limitations, okay? If we're not going to be able to form a cation, then, we can't really go through this method of adding an alkyl chain. We'll talk about that in just a bit, though, right? And we do have to pay attention to rearrangements, all right? Rearrangements, hydride shifts, alkyl shifts, all this kind of stuff can happen here. That is our limitation. If we can rearrange, we will rearrange. Okay, that's just the name of the game. That's how the cations work, right? Always they're going to go towards the lower energy state of the cation there. All right. This is going to be a catalytic reaction. And so I think at this point, as we get a little bit further along into the organic realm, we can start to understand why I'm starting to point this out. Remember, as soon as I say that something is catalytic, that means whatever we put in there at the beginning to get the reaction going means it's got to be reformed at the end, right? And so here we are going to be using a Lewis acid again. All right, and so I know I've made this point before, and I've talked about it in the other videos and all this kind of stuff, right? An acid, whether it's Bronsted or Lewis, are typically always going to be used at the start of a reaction mechanism, all right? And that's going to be the same here. As I said, if you guys are kind of skipping around in my videos, I'm trying to, I'm trying to make these stand alone by their own, but some of you guys might tackle these in different order, right? Remember, in the 3 steps for the mechanisms that I talked about in my other videos about nitration and, goodness, what's the other video I just posted? What did I do? I did nitration, and then the, the halogenation. Yep, sorry. Had a little slow moment there, right? So in my videos about the nitration and the halogenation reactions, remember we used a Lewis acid in both cases, and they were used in the first step. It's not going to be any different here, okay? We can use a variety of different Lewis acids. AlCl3, okay? We saw this in the halogenation reaction, okay? This is probably going to be the most common one. Just because it's cheap and pretty easy to use, and there's nothing too involved with it. I shouldn't use purple here since we're kind of in a subheader. Common things are also titanium. Whoa, that wasn't anything there. Titanium chloride, or I should say titanium 4 chloride, or zirconium chloride, or zirconium 4 chloride, right? Titanium and zirconium are in the same family on the periodic table, right? So that's not too surprising. You might see those. You can use a couple other transition metals also, but I mean, by far, and what we'll be using for the most part is aluminum. Titanium is really, really moisture sensitive, and so it's kind of a pain to use, just practically speaking. It's not that bad. It's not that it catches fire or anything. It's just it's really sensitive to moisture, and as soon as it gets in contact with any water, it's going to decompose into titanium, into titanium oxide. And as just as a quick this and that to kind of break up some of the monotony of these videos, maybe this is actually what they used to use for skywriting, titanium chloride. As soon as we add some water to that, right, it turns into titanium dioxide or titanium 4 oxide, which is a brilliant white powder, and so they used to basically spray titanium chloride out the back of the plane, and it turns into titanium dioxide there, which slowly settles down to the ground as a brilliant white powder, so it's reflective and easy to see from the ground, that kind of stuff, right? Titanium dioxide is found in a lot of cosmetics, in sunscreens and things like that. White paints tend to have titanium dioxide in it just because it makes a very shiny, brilliant white color. The realm of paint chemistry and color chemistry is a white color is not the same as a white color is not the same as a white color. And if any of you guys have ever owned a house or tried to paint a house, right there, you go to the store and say, well, I want a can of white paint, right? And they say, okay, what kind of white? And then there's a billion colors, and I lose interest, and whatever, right? So just as a brief aside, right, there are a lot of uses for titanium, and I do want to just remind you guys that I show you guys one way or two ways of accomplishing some of these transformations. But if you ever go look it up online, and there's some fantastic resources there, we see there's actually a lot of ways to accomplish even something like a Friedel-Crafts alkylation, right? And the reason why I mention that is that there are certain cases where you do have to use titanium or zirconium rather than aluminum, all right? So the point being is that, remember, as we have different functional groups present, right, then we have to take care of selectivity, and aluminum does certain transformations where titanium won't, and there's all these considerations to take place. Right? So I teach you guys the most common way, and I just try and kind of bring in some of this other information for the other things there, right? Okay, so let's move on from this. Let's figure this out. Here is Mr. Generic reaction. This is probably the quintessential reaction. We used to do this in the lab, actually, as one of the undergraduate. You know what? Let me draw this a little bit bigger here. We used to do this in the undergraduate labs as one of the standard reactions that we did, just because it's a very, very common reaction, right? And it's pretty easy, pretty straightforward, right? We can get our aromatic ring, benzene in this case. We find some kind of alkyl halide, okay? And then we just we scoop in some aluminum chloride, and we come back and clean up our product is what it is. And when we do this, right, we will add that alkyl group to our aromatic ring. Okay? Cool. That's it. That's how this works. So now we're going to break down this mechanism here, right? So as always, the colors I've been using have been yellow for the first step. I should write these down somewhere so I don't get them messed up. But anyway, right? So let's get this going. So first step, right, is generate the electrophile. This is going to be pretty similar to what we've seen all along. Right, we have our Lewis acid. The Lewis acid has an open p orbital. Right, we're going to end up binding the halogen to that. I'm going to kind of pause here for a second. Right, I'm going to draw the rest of this stuff out. Let me see if I can maintain a proper geometry here. That looks nice, super fancy. Alrighty, right? So if you pause here for a second, right, or if you take a look at this for a second, right, this setup looks pretty darn similar to what we saw in the halogenation mechanism, right, where we end up seeing a chlorine with a positive charge there. It's bound to the aluminum with a negative charge. Obviously, that means that we are weakening, right? We're weakening this bond here, right? And so that's going to be what happens, right? Basically, that bond's just going to snap, right? Well, not snap. I think you guys know what I mean, right? We're going to end up breaking that bond, right? And so then we make our buddy aluminum tetrachloride, right? Cool. And there it is, okay? So now we have generated our very good electrophile. Right, there's our very good electrophile. Now I gotta pause at this point, because at the end of the day, right, I know it's gonna. I'm gonna use. I know you guys can visualize me already, right? I know you guys can't see my face because I don't record video with these, because otherwise you guys would be basically looking up my nose, right? Because I got to set my laptop down, right? But anyway, in my mind, right, I'm doing my professor magic trick where I'm reading your guys' mind, and I'm looking into the future, and I'm seeing what can happen on the next exam. And you guys are going to generate a carbocation, and you guys aren't going to stop, right? You're not going to think. And then you're going to get big sad face, okay? Or angry face even. Because remember, what I asked you guys to do is stop and think every time you generate a carbocation, right? Can I rearrange? Can I shift? Can I do any of these kind of things, right? So, same thing here, right? We stop and think if there can be, I think I wrote it up here, right? Right? Or I talked about it here at least, right? So, if there is, or the possibility to do a rearrangement, it will. So stop and think, okay? Consequential, or, oh my gosh, I'm failing at talking today all of a sudden. Consequently, right, this is why I show you guys this reaction, right? Using this T-butyl chloride here, right, we generate a tertiary carbocation, it's not going to shift, right? There's not going to be any rearrangement in this case, right? It's easier to generate a tertiary carbocation, it's not going to shift in this case, so this is a pretty straightforward thing to do, right? All right, hopefully I've made my point with that. All right, let me zoom out here. What color did I pick for the next two steps? I believe it was green and then black. Yes, it was. All right. So now that we've taken care of generating our electrophile, right, we'll go on to the next step. All right, now let's use that. All right, remember the next step is where our aromatic ring attacks the generated electrophile from the first step. So I'm just going to bring down my tertiary cation there. There it is. Pi bond swings open. I'm going to, right, make the same point I have been making, because again I am predicting the future here, right? This is going to be one of those other points that gets missed on the exam. which hydrogen, right, gets removed to reform the aromatic ring, right? That's just one of these things that seems to happen. Positive charge here. Okay, so there we go, right? This was our second step. The aromatic ring swings open, grabs the nice electrophile that gets generated there, right? And then the last step, right, here's what I was just talking about. Here's the step that gets missed. Remember, it is the hydrogen bound to the carbon where the functional group is added. That hydrogen in black, right, that is the one that gets removed. Okay? Remember, this is catalytic, right? That means we have to reform the stuff that started out this reaction. So I'm bringing in my aluminum chloride. The aluminum chlorine bond breaks, right? Grabs that hydrogen, and that forms our aromatic ring again. Okay? So you can pause here and see if you can get to the answer before I can. Whoops, that didn't change colors. Green here, our green pi bond is reformed, right? And we added this butyl group right here. Okay. We reformed our AlCl3, and then we also happen to form some HCl. Right, that bubbles out of our solution. And so this, right, this step here, right? This step here is the reforming the aromatic ring, right? So the step in black there. That's it, right? There's not a big mystery to this. That's how this mechanism works. Hopefully you guys are starting to see this pattern again, right? The mechanism isn't that complicated in this case, right? We just have those same three steps again. Generate electrophile, attack with the ring, reform the ring. Okay? The thing to pay attention to is forming the carbocation. Make sure you can. Alright? And check out for any rearrangements. Now let's think here for just a second. Okay? Let's say we have this situation here. Right? So now here's our product. Okay? Now see if you guys can pause. All right, I'm going to pause here in just a second too, right? So see if you guys can pause and work through this mechanism before looking at what I'm doing with it, right? So take a quick second pause here. I've got to pause on my end in real life here, and then see if you guys can work through this mechanism before I do it. Now you got to stop and think, right? Please stop and think. Work through the mechanism. All right, we'll be right back. Alright, so we're back here. Let's hammer through this mechanism, right? Right, generate the electrophile. Now take a look, right? This would form a primary carbocation. Are we going to form a primary carbocation? No. Right? So we're not going to form a primary carbocation. We're not going to violate the rules. Right? We're not going to violate the rules that we learned. The primary carbocation is really not going to form unless there's a very, very good reason, which right now we don't have a very good reason. Okay? So in reality, right, this blue bond here, this does weaken that blue bond, right? So that in the next step, right, this can come in, right, and basically knock that off. Let's see, we made a bond in red to our carbon in purple. Right, we got that on there. Generate the positive charge. You guys see where this is going already, right? Now we have to regen our aromatic ring. So we come in, we do that, and there we are. This was in red, this was in green. Okay. So in the case of primary carbocations, right, this can still work. It'll be a little bit slower, right, than the tertiary for the same reasons that we discussed before, right? Or I mean that we discussed previously when dealing with carbocations. But we won't generate a full carbocation. We'll have this kind of intermediate, equilibrium species there where that carbon in purple is more susceptible to attack, right? Okay, so I think this is a good place to end this particular video. The next video, we're going to continue on with our discussion of Friedel crafts. We'll talk about some alternate methods. We'll talk about some limitations. We'll look at some of the rearrangements and things like that. Okay? Alrighty.